this is the solution to the second problem in our fluid dynamics practice problem set. So we have a fire hose. There's a certain flow rate. We're given the flow rate. The flow rate is 40 liters per second. And we know that the hose tapers from a 9 centimeter diameter fire hose to a 3 centimeter diameter nozzle. And we're asked to figure out the pressure drop as the water goes from that 9 centimeter diameter hose to the 3 centimeter diameter nozzle. Let's draw a picture. So here's our hose, and it tapers down to a nozzle like this. So we know that the diameter here is 3 centimeters and the diameter here is 9 centimeters. And our flow is this way, and we just know the flow rate. So the flow rate is Q, and the flow rate is actually related to the cross-sectional area times the speed. Okay. Right. But before we get that, liters per second is not our SI unit. We want this in meters cubed per second. So if we convert 40 liters per second into meters cubed per second, it actually becomes 0.040 meters cubed per second. Okay, so we have our flow rate. It's related to the cross-sectional area times the speed. We can solve for V. V is just the flow rate divided by the cross-sectional area. Great, so all we have to do is figure out the speed of the water through each of the sections, through the hose and through the nozzle. So let's go through the 9 centimeter hose. The speed of the water is the flow rate, which is 0.040 meters cubed per second, divided by our area, cross-sectional area, which is 1/4 pi, times our diameter, which is 9 centimeters. Oh, we want that in meters, though, don't we? So let's just erase this. And we want 0.09 meters squared. There. Okay, and this ends up becoming 6.29 meters per second. Good. Okay, now, what about the speed through the nozzle? So that's through the 3 centimeter diameter cross section. Note the flow rate is the same. It doesn't go any faster or any slower through the smaller. You still have the same volume of water flowing through the nozzle as you do the hose. So we use the same flow rate, and we divide by our new cross-sectional area, which is 0.03 meters squared. And you should get a flow speed of 56.6 meters per second. We know the water should be flowing faster through the nozzle than the hose, so these two values make good sense. Okay, so what we were asked, though, is to find the pressure drop. Well, so what we're going to do is we're going to turn to Bernoulli's equation for that. So from Bernoulli's equation, we know the pressure through the 3 centimeter diameter nozzle plus the rho times g times the height of the 3 centimeter nozzle plus 1/2 rho v cubed squared, not v cubed, v3 squared is equal to P9 plus rho g y sub 9 plus 1/2 rho v9 squared. Okay, so basically the left-hand side is dealing with the nozzle, and the right-hand side is dealing with the hose. What we want is we want P9 minus P3. We know the pressure in the hose should be greater than the pressure in the nozzle, because the water is flowing faster through the nozzle, there's less pressure. So this change in pressure should be positive. We know we can assume these things are at the same height, so those two terms will cancel, and what we're left with is 1/2 rho V3 squared minus 1/2 rho V9 squared. Great. So those two speeds we just found previously, so we can plug those into our equation. So we have P9 minus P3 is equal to 1/2 rho, which is our density of water. Our density of water is the usual 1,000 kilograms per meter cubed. And we multiply this by the difference in the square of the velocities, so 56.6 meters per second squared minus 6.29 meters per second squared. Good. And this pressure difference is going to be to 3 sig figs anyways, 1,580,000 pascals. Good. So that's the answer to A. So B, to what maximum height above the nozzle can this water rise? Well, there's a couple ways we could do this. So the water is flowing out of the nozzle. It's flowing at a certain speed. So if we shoot this water straight up with speed 56.6 meters per second, we can use conservation of energy actually. So we have 1/2 mv squared is equal to so that's the kinetic energy is equal to the potential energy. So all that kinetic energy gets converted to potential energy. So that's equal to mg times the height. If you look at this, the masses cancel. And so we can solve for the height. The height is just going to be 1/2 times v squared over g. And well, we know all of the numbers here. So it's 1/2. The speed is 56.6 meters per second squared over 9.8 meters per second squared. And the height we get is 163 meters.